All right. All right. You guys see my screen okay? Okay. All right. Oops. Where is it? Okay. Hopefully that worked. All right, guys. Today we're going to work through 7.3, which is properties of the Laplace transform. So if you remember, I'm going to go back to 7.1. The idea with the transform, at least the way we're going to use it, is we're going to use it to basically bypass all of the crazy work we've had to do for solving differential equations. So if you stay in the T domain, you got to do a bunch of stuff. But if you move into the S domain, your work's a lot easier, but you have to learn the transform well. So what we've been doing in 7.2 is really focusing on this part, right? Translating from functions in the T domain to functions in the S domain. And, we define the transform. You guys have some homework on it where you have to do that for some specific examples. I sent out an announcement about making sure to do the transforms by definition if they ask you to. If it says by definition, what I mean or what they mean is to do it like we did, let's say in example 2, for example, where you have to write out all this stuff. But pretty soon we can kind of let that go and you guys can use the tables. All right, but if it says use the definition, that's what they mean. So in this section, we also discussed the linearity of the transform, which is really helpful. And we also discussed the existence of the Laplace transform. There's a couple of conditions that you can put on the function. If the function is piecewise continuous and it has exponential order alpha, then the Laplace transform exists for s greater than alpha. So yeah, that's where we finished off last time. And then if you're interested, here's some more theory. Okay. So today we're going to talk about properties of the transform, and it's still kind of the same goal. Our goal is to basically transform functions from the T domain to the S domain. So it's kind of the same thing, but there's a lot of stuff that we still need to work on. So if you go back to section 7.1, where I gave you the idea of the transform, remember this is the IVP we were trying to solve. And the idea is you want to transform everything inside. There's a bunch of functions in there. So we want to transform all of them into the S domain. So like the X gets transformed into a capital X, and the little g to the big G, and the X prime, we haven't talked about how to transform a derivative. So we're going to talk about this rule today. There's also one for the second derivative and third derivative, and there's a pattern. So that'll be helpful. So that's one of the things we're going to talk about. And yeah, that's the main one. So also translating is going to help us too. Okay. All right. So yeah, so solving these things by definition, it can be really tedious. So what we want to do is come up with as many different ways of saving time. The Laplace table is only going to work for some of the problems, but if we can come up with some other properties to help us, then the Laplace table and those properties hopefully will be enough to handle just about all differential equations, or all functions we'll run across. All right, so let's start with this one. So let's say that you have a function f. Okay. Now, and let's say that you know the Laplace transform of f. So let's say you figure that out by definition, or let's say it's in the table already and you've already done it. And let's say it exists for s greater than some alpha. Well, it turns out that if you want to take the Laplace transform of f multiplied by e to the at, it turns out that what you'll end up getting is you'll get a translation or a shift of the function of the transform without the e to the at. So essentially what that means is if this takes you to f of s, this is going to take you to f of s minus a. Okay, essentially you're going to replace the s here with s minus a. That little a right there is basically performing a shift. So e to the at is shifting the transform. And then when you shift, one of the things is the domain changes a bit. If the domain started out as alpha, you're going to add that a to it. So it's now going to be a plus alpha. Okay, so put simply, if you multiply a function by e to the at, all it does is it translates, it shifts the transform either to the left or to the right, depending on the sign of a, and also shifts the domain. Now, it's important we go through this proof just once. It's not a hard proof, but just to see it, to prove it to ourselves. And then once we've proven it to ourselves, we can use it whenever we want. So here's the proof. It's pretty short. So this is what we're trying to find. So we'll start with that on the left. Okay, so what we're being asked to do is find the transform of this function. So I'm going to just do this by definition. I'm going to take this function and I'm going to plug it in right there in red. I'm going to multiply it times e to the negative st, like we always do for a transform, and we'll evaluate that improper integral. The nice thing about this, though, is that these two guys combine because they have the same base. So if you combine them, you'll get this guy. All right. But then this guy is just the transform of f of s minus a. If you take your old s and replace it with s minus a, that's exactly what you get. Okay, so what we've done is we've proven this theorem. So now that we've proven it the long way by definition, now we can use it. So let's try it out. All right, let's say we want to take the Laplace transform of sine bt and it's being multiplied by e to the at. Okay, so basically we're going to prove a rule that's in our transform table. Okay. So we already know, let's say that we know that the Laplace transform of sine bt is b over sine squared plus b squared. I think we might have proven that one too. And it's valid for s greater than 0. Then when you multiply by e to the at, and you see where that transform does, all it's going to do is translate this result. So instead of going to an s, that s is going to be shifted. So now it's going to be s minus a. Okay, so if we go in, you let f be the function, there's the transform of, if you let f be this function, right? That's the transform on the table. So if you want to find this guy, you would just use this transform, which is for sine bt, but plug in an s minus a there, right? If you plug in an s minus a, that's what you get, right? Okay, so that's all it is. It's just a horizontal shift. And we started at 0 in a domain for s greater than 0. So all we have to do is add a to it. So this is our rule, or this is our conclusion for the Laplace transform of e to the at sine bt. That okay? Okay. For you mathematicians out there, this is the kind of stuff that you're going to be doing. Once you get past differential equations, it starts moving it more into the theoretical world. And so you're going to be proving a lot of stuff like this. So it's good to try and get a handle on this and see if you can follow the proofs and get some ideas. All right, so that's translating. So that's one thing that'll help us. If we ever multiply by e to the at, it's just going to translate the transform of f of t. All right, so what about these guys? You know, sometimes you're going to want to take the transform of a derivative. In fact, that's exactly what we want to do over in 7.1. when we translate, where is it? This IVP, one of the things that we want to translate is that function right there. I'm sorry, transform is that function right there. So, and we don't, it would be nice if we didn't have to go through the definition to do it. So I'm going to show you why x prime of t gets transformed into that guy. It's going to require an integration by parts. All right. Oh, not that one. All right. So here's the rule. If your function's continuous on the standard time domain, 0 to infinity, and its derivative is piecewise continuous on the standard time domain, and both functions have exponential order, which basically means they can't grow above a certain limit, right? Okay. I would say they can't grow faster than an exponential function. That's a better way of saying it. Then the conclusion is that if you take the Laplace transform of the derivative, it's equivalent to s times the Laplace transform of the function minus the function evaluated at 0. This is where your initial conditions come in. So I mentioned this back in 7.1. It's weird that you would take an entire IVP along with the initial conditions and you transform everything, including the initial conditions. And the reason why is because of this theorem here. Okay, and this thing's valid for s greater than alpha, and that's because of the order on the functions. Okay, so if you think about basically what this is saying, it's saying that if you want to take the transform of a derivative, you can do it and you can express it completely in terms of the transform of the original function, which is what you want to do, because we're creating a polynomial in terms of the original function, like y or whatever it is. So you want to have only y's in there. So we got to knock down this derivative down to just our y. Okay, so let's look through the proof. Again, this is one of those things where it's important to see just so we know what we're doing. So here we go. We're going to start on the left here. So by definition, you're going to take the f prime and just plug it into the definition. Is that okay? Okay. All right. Now, by definition of what an improper integral is, we change that to an n, and we take the limit as n goes to infinity. Is that okay? Okay. Now for the little difficult part here. You'll notice inside here, we've got two functions of t. Function of t times a function of t. And we're asked to integrate that. So whenever you run across a product of two functions, two variable functions, what method do we use to integrate?
By parts.
Yeah, we use by parts. So this one's a little trickier just because it has, an integral and a limit there, but you just push them through. It's the same thing. Okay, so if you were to do this by parts, and you guys could do this on your own, what was it? Integral of u dv equals uv minus the integral of v to u. So there's your uv, and there's your minus the integral of v to u. And there's a negative that cancels out, so you end up getting a positive there. Okay, make sure your limits are on there and your limits of integration show up too. All right, so then what happens here? Let's see. We want to evaluate this guy from 0 to n. So you're going to plug in an n and plug in a 0 for t. So if we plug in an n for t, we're going to get this guy. If we plug in an n there, okay, so there's plugging in an n for t. And if we plug in a 0 for t, we'll get this guy, and we just subtract the two. And we take the limit of that result. Now over on the right, you'll notice this integral is with respect to t, which means that the s is a constant as far as the integral is concerned. So we can pull it right out the front like so. Okay, so we'll leave that alone for now. All right, then you might notice this. What's e to the 0? It's just 1, right? So this guy kind of disappears. He turns into a 1. And then this limit over here, Isn't that just the Laplace transform of F? That's by definition, right? So we can replace that guy. Okay, so really all we're left with, we've got the Laplace transform of F prime equals, and it's going to be this is just going to be F of 0. And that's just a number, right? We don't have to take the limit of it. But we still have to take the limit of that guy. So I'll leave that one in. I'll put it in blue because that's the difficult part. Okay, so let's keep going. Now, one of the things we were given in the theorem is that, let's see, f of t is of exponential order, right? Both are of exponential order. So what that means basically is there exists a constant m such that for n large enough, we can state this. Right? I'm just pulling this from our discussion on 7.2. It's exactly what we were talking about in there. I can put a bound on this exponential. Where is it? On this guy, on f of n. Okay, so it's bounded by an exponential function. That means there exists some n and some large enough n so that all of these guys are trapped below these guys. That's the whole point of what exponential order means. Okay, well, we could simplify this. These two guys combine, this one and this one. We can combine them into that. Okay, so what does this mean? Well, now that we've got this inequality, and I know that this guy is less than or equal to this guy, this is definitely positive, right? It's greater than 0. How do I know this is greater than 0?
The absolute value bars.
Yeah, absolute value bars, right? So what I could do here is I could put a 0 there. Is that okay? Okay. So look, once we have this inequality, what we can do is we can apply the limit through the whole thing. So the limit of 0 as n goes to infinity stays at 0. This is the limit that I'm after, this one right here. So I'll just push the limit through this guy. And this guy on the right, that limit right there, you guys can do this one. All right, we know S is greater than alpha. So what happens is this exponent gets increasingly large negative, which means that this whole thing goes to 0, which means that this zeroes out. So if you look what we have 0, and then we have this thing inside that we're interested in is less than or equal to, and then there's another less than or equal to, and then a 0. And just by straight up logic, if that thing is between 0 and 0, this has to be 0, right? Okay, so that means that that's the squeeze theorem from calculus 1. So we've squeezed this thing. We know that limit is 0, which means this guy is 0 right here. Okay, or this guy. All right, so that means that guy is going to 0 out. And then hopefully you can see what's left over. That's our rule, right? So we'll state it around here again. And that's the rule for taking the Laplace transform of a derivative. All right, that's the kind of stuff. If you guys go on in mathematics, you'll be working with a lot of that stuff, and you make them yourself. So it's difficult, but it's kind of fun once you get them. All right, so that's great. Now we know how to take the Laplace transform of a derivative and knock the power down, or knock the degree down, or I should say order down to just the regular function. But sometimes we're going to have to take the Laplace transform of higher order derivatives. In fact, the one we did in 7.1, that was just first order, but you could really do it for any order. So you can apply the rules of mathematical induction. Have you guys heard of mathematical induction before? Okay, well, it's a really powerful rule. You guys are supposed to have learned it in pre-algebra, or pre-calculus, I should say, and probably seen it in algebra, but it's a way of proving things infinitely. So for example, if you have an infinite staircase, okay, and you want to prove that you can climb the infinite staircase, you'd have to show two things. The first thing you'd have to show is that you can get to the first step. Okay. The next thing you would have to show is this. If you can get to a step, then you can get to the next step. Okay. If you put those two things together, you get to the first step, applying the second rule gets you to the next one, applying the second rule again gets you to the next one, and you could prove it off to infinity. So it's the same thing here. It's, if you have a chance, you might want to watch a video on it. It's a really nice tool to use when you're trying to prove things for, you know, an infinite list of things. In any case, you can take this rule and you can extend it up to higher order derivatives. So here's the rule. So it's kind of the same conditions for starting. You have to have, you know, continuity and piecewise continuity and exponential order alpha for all these functions. But here it is. If you want to take the Laplace transform of an nth order derivative, you're going to take s to the n. We've knocked it down to a 0th order derivative, which is the whole point. You have to get a 0th order derivative in order to solve that algebraic equation. And then you have basically a bunch of this garbage left over. Okay. Now, if you think about what that garbage is, it's basically a polynomial in S where the coefficients are all of the initial conditions. Okay. Now, what you want to notice when you're looking at this is patterns, okay, to help you remember. Okay, so you notice up here when we did the first order derivative, which is just a special case of this, I put a single s there, first order. You notice this is an nth order derivative, so we did a s to the n. So does that make sense? Okay. The next thing you'll notice is that they both involve f. You know, sometimes I put in the t, sometimes I don't. I guess I'll put it in here. It's just function notation. Okay, so the next thing to notice is that you've knocked it down to the Laplace transform of just the original function itself. All right, then. After that, what ends up happening is you decrease in the degree of the power of s. So s is going to go down in degree. But then the initial conditions are going to go up in degree. Okay, so this is f of 0, which is a 0th order derivative, and then f prime would be the next one. Next one would be f double prime, all the way up to the n minus first derivative. And there's no s term on this one. They knock out. In fact, I can write in the next to last one. What would that be? There'd be an s in there, an f. To the, let's see, n minus 2. Okay, just so you can identify the pattern. And by the way, this is just a special case of that. It's just the case where n is 1. All right, so play around with that. Okay, so let's look at an example. So this is just going to be a first order example. So let's say that, let's say we don't know this transform, like it's not in our table, and you wanted to find it. And let's say that we were given this transform. So basically, we're going to avoid using the definition by using this rule up here. This one right there. Okay, so here we go. So do you guys recognize that as the derivative of something? It's the derivative of 1 over b sine bt. Okay, so that's the way to think of it if you want to use the rule. So so there's a couple ways to go about it. You know, I went about it this way. I let f of t be sine bt, and that means that f prime is b cosine bt, and then I handled the 1 over b at the end. So by theorem 5, we know that the Laplace transform of b cosine bt, which is f prime, is and that b cosine bt is the derivative of this guy. Okay, so the derivative is here, f prime, and f is there. All right, so you'll notice that it's first derivative, so I put an s in front. And then this guy right here, well, that's just f of 0. That's your initial condition. And since f is the sine function, you'd have sine of b times 0. And the sine of b times 0 is 0. So that guy's going to drop off. All right, so what we're left with is this guy for s greater than 0. So then what we can do is we can divide both sides by b. And now we have our conclusion. Now this rule is in your transform table. It's one of the many rules. And the idea is we're developing those rules using these theorems. Is that okay? All right. Now this one's probably, the notation is going to be a little heavy. Okay. You guys ever seen something like this before? You notice I've got a fixed number there and I've got a variable there, right? All right, you see that little tau symbol? It's just a symbol. It could have been anything, right? I didn't use a t there. Why do you think we didn't use a t there? There's a reason why. Anyone? We've already have a t there. We can't use a t twice, because once you find the antiderivative, right, you're going to have to plug in a 0 and a t, and then you're going to have multiple t's. So it just doesn't work. So what you do when you have this situation, I mean, when you have a variable up there, just make sure you don't use the variable when you're integrating. Okay. So, and it doesn't matter. It's a dummy variable anyway. It can really be anything. It could be an X, a Z, smiley face, doesn't matter. Okay. So, but this indeed, that's a function, right? It's called the area so far function. You guys have seen this before. You saw it back in Calc 1. What it does is it finds the area from underneath the curve of f from 0 up to t. It finds the area underneath it, right? If this was a 3, it's the area underneath the curve from 0 to 3, right? Underneath f. But if it's a t, now it becomes a variable function. Okay, so now that I've got this function, oh, and by the way, what's the derivative of this function? Remember the F fundamental theorem of calculus part 1. This is back in Calc 1.
Isn't it just f of tau?
Yeah. Actually, it's f of t though, right? Because you're gonna, it's f of t, right? Because this right here is actually a function of t. Once you find the antiderivative and then you plug in the 0 and the t, it'll turn into a function of t. So then when you take the derivative of a function of t, you get another function of t. Essentially what this is the fundamental theorem of calculus part 1. Right? The fundamental theorem of calculus, if you think about it, the big idea, all it says is that if you have a function and you integrate it first and then differentiate it, they kind of undo each other. And then it also says, the part 2 and part 1, they both say if you switch the order and you differentiate first and then you integrate, they cancel each other. And that's all this is saying. It's saying if you start with a function f, right, and then you integrate it, turning it into a variable function of t, and then you differentiate it, you get back the original function f. That's all the fundamental theorem of calculus basically says. Okay, so we're going to take the Laplace transform of this function. Okay, because that is a function of t, so I'm going to place it right in there and we're going to take it. We're going to take the Laplace transform. Okay, now we just talked about how to take the Laplace transform of a derivative. So maybe we're going to use that here. Okay, so, and it's very easy to differentiate this, right? Okay. All right, so we're going to prove this statement. I'll get rid of the S. We don't need that stuff. Okay, so here we go. And then we'll use it to verify example 2. And okay, here we go. So what I'll do is I'll let G of T be this function here. Okay, so like you said, if you differentiate it, you get F of T. Okay, so what I'm going to do is I'm going to apply theorem 4 to this, which is this guy. Okay. All right, theorem 4 says that if I take the Laplace transform of G prime, I'll get S times the Laplace transform of G minus G of 0. Let's plug it in. Okay, so let's start with this actually. G of 0. What does G of 0 mean? Well, I claim that it's equal to 0. So if this is the G function, what happens if I plug in a 0 there for T? Zero here, makes that a 0 there. So what's the integral?
0.
0, because you're integrating from 0 to 0, there's no area. Okay. So this guy, that negative G of 0 is going to drop out. And this G of T right here is that integral. So I'll pop it right back in. I'm going to take both sides of this equation. I'm going to divide both sides by S, which will allow me to isolate what I'm trying to find. This is really what I'm trying to find. So there it is. If I divide by S, I'll get 1 over S times the Laplace transform of G prime. But we all know what G prime is. G prime is really F. Okay, so far? All right, so, and that's what we were trying to show. All right, gets kind of confusing with the notation. See if you can kind of work through it. All right, and then you can use this, let's see, use it to verify the solution to example 2. Yeah, Laplace transform of cosine BT. Where we are, there we go. So, where are we? Verify example 2. Note that sine BT equals, okay, so what we'll do is we'll express sine BT in terms of the integral of 0 to T B cosine beta tau dt. Let's see. I lost my train of thought. Or if I know. Well, okay, so these are the same thing. They're really the same function. If you differentiated them, that should be 1 over b. Hold on a second. Yeah, I think I made a mistake here. Maybe that's why I'm confused. Because if you differentiate this, you'll get b cosine bt. Yeah, that's not right. Okay, I'll just skip this one. I'll fix it in the notes later, okay? All right. All right, so there's one other thing that might help us from time to time, and that's derivatives of the Laplace transform. So you might wonder, like, what happens if you take a Laplace transform and you take its derivative? Is there a way to relate that to the original function f of t? And it turns out there is. The derivative is related this way. It's a Laplace transform of negative t times the original function f of t in the t domain. And you can take this idea and you can extend it up using the induction principle. And then this nice pattern develops. So here's the pattern. Basically says, if you take the Laplace transform, we're kind of going in reverse now, but switch sides. But basically it says, if you take the Laplace transform of function times t to the n. So that's the thing that we're curious about. What happens? Right? Well, what happens is the signs oscillate depending on the order of n. So there's your oscillation in sign. And then what it does is it increases the order of the transform, the order of the derivative of the. Okay, so this is going to help us in those specific situations when you have an extra t to the n and it's not somewhere in your table. All you have to do is take what you know, take the derivative of what's in the table n times, and make sure to flip the sign a few times appropriately. All right, so yeah, so we'll take a look at that one. Use theorem 6 to determine. Okay, so we've got the Laplace transform of sine bt. That's pretty standard one. You're going to see that in every Laplace transform table. But depending on the complexity of the table, you might not see a t in front. They might not have a separate one for that. So this is a very basic one. We've got this situation definitely where n equals 1. So what I'll do is just use the formula. All right, so here it is. All right, so I already know that the Laplace transform of sine bt is b squared over sine squared plus b squared for s greater than 0. So by multiplying by t, the new transform is going to go to -1 to the first, and then times the first derivative. That's important, right? For this case, because it's n equals 1, the first derivative of where it was going before. Okay, and this is where it was going before without the t. Okay, so then all you have to do is differentiate this with respect to s. It doesn't change your domain, and this simplifies like so. So this is the Laplace transform. Okay, now we've been doing a bunch of these so far. Have you guys noticed that all of the problems, that all of the transforms we're getting, they're all polynomials in S over polynomials in S? The B's are constants, right? We know what the B's are. But if you look at every single one, they're all polynomials in S over polynomials in S. Okay, so if you're interested, I know a few of you stayed afterwards last time, but if you're interested in how that relates to, let's say, the mass spring oscillator, I put in a couple optional, there's an optional video and there's also some notes on that before. But just so you can see kind of what's going on. I don't think you guys are going to see the code. Here we go, predicting, okay. So like if you have something like, there's a Laplace transform, we got a polynomial over polynomial. The top is never 0, but the bottom is 0. Where's the bottom 0? For what value of s?
-3.
-3. So what ends up happening, if you were to read through what's above, you'll notice that there's going to be a pole. We can graph that pole at -3. This is where the function blows up. That's why we call them poles. You can graph the pole in the real imaginary plane. And looking at these types of diagrams, you can tell what the function is going to do. So because it's on the real axis, you know that your function must be completely exponential. And in fact, there it is right there. It's in the Laplace transform table, but it's e to the -3t. And in terms of the mass spring oscillator, this is overdamped or critically damped motion. So if you have something like this, polynomial over polynomial, it's got no zeros in the top, but it's got a 0 in the bottom. What are the zeros at the bottom? What values of s would I have to plug in to make the bottom 0?
2i.
It's never. Yeah, that makes sense.
Yeah, so so that's the thing. We've been so used to working with the reals that it seems like it's impossible, and it isn't. So I didn't tell you this, but if you read through above, what you do when you're working with a function like the Laplace transform is that function is a complex function. So we have to take complex numbers to complex numbers. So you have to allow for complex numbers. So if you were to factor this over the complex numbers, it would look something like this. Right? Okay, so now there's no zeros on the top, but on the bottom, there's some roots there, and those are going to cause the function to blow up. So they're happening at 2i and -2i. So you can graph them. They're always symmetric because they come in pairs like this. And if they're completely on the imaginary axis like this, what you know is that your motion is sinusoidal. In other words, you have harmonic motion. There's no friction. Okay, so in fact, if you use the table, There it is right there. And the 2 corresponds to the poles. And then if you wanted to mix them and do, let's say, exponentially damped or under damped motion, right? You'd have something like this. You'd find the poles of the zeros at the top and bottom. You'd plot them, and you'll notice that your zeros on the real, that gives us our exponential right there. And our poles are off in the complex space. So they're partly exponential, partly imaginary. So, partly sinusoidal. So what you can do is you can use your transforms to predict the nature of what happens in the system. So when you see something like this, you'll be able to tell like, oh, that seems like a reasonable answer. Okay, so if you're interested, go watch that video, read through the notes. The last part of this is just a summary table. So let's go through it real quick, and that'll be it. So these are some of the properties that we're going to be using moving forward. Remember, our goal for this whole section is this part, translating from functions in the time domain to functions in the S domain. Okay, so that's what all this is about. Laplace transform is linear. That gives us the first 2, right? Okay. This is that translation property, right? If you multiply it by e to the at, it just shifts the transform. This is that first derivative property. Notice the s, notice the minus f of 0. This is the second derivative. They broke this up just because these are common. We do a lot of first and second order ones, but you can see the pattern, and this is the general pattern using induction. And there's what happens when you add in that power function at the end. It just flips the sign. All right, guys, let me stop the video here.